Welcome everyone, this is Mr. 13 Things. Welcome to our second tutorial or video on how to use the TI-83 calculator to do things like animation. As a demonstration, and what I'm going to do is I'm going to go ahead and try not to erase my things across the top. I am using something called Smooth Draw 3.0 and Camtasia to do this editing. I'm going to cut that. You cut off my calculator. I'll cut this off here, and I'll bring another edit, cut. So we're going to talk about using the TI-83 calculator as a good entry point, though not really what I would call modern technology. I would call it perhaps getting on the order of antiquated, but still allowed on the ACT and the SAT. So that still, it would appear for many, tends to be the gate. The gate, you know, into a lot of different things is that you can actually apply some algebra, math, etc. And so this TI-83, TI-84 Plus is allowed on that. So what we're talking about here is simple animation. So simple, and I'm going to talk about here is vector animation. Now, we'll also talk eventually about raster. The same thing, animation, but we're going to start and really begin with this concept of vector animation. And what we're going to do is we're going to remember that we can define anything, a shape, right? Can eventually be busted into triangles, if you would. We don't always have to do that. Triangles, of course, are going to be vertices and edges. And vertices are defined by a vector that is x, y, and z, typically, even if the z is 0, and then what we would call a 1 chaser or a scale factor of 1. And we can stack up a number of vectors, right, in kind of a position matrix so that it looks more like this: x1, y1, z1, 1, x2, y2, z2, 2, and x3, y3, z3. Those are actually ones, 1, 1, 1. Though eventually you might want to actually start talking about giving a name to each of these point vectors. Okay, so that's a big leap for people to make because they're used to doing what? X, comma, y, comma, z, and not writing things in a stack of a column vector. But it's more standard when you get into most applied mathematics and graphics to think of things as vectors, column vectors. All right, so that said, how do we go about using this to do animation? Well, one of the big parts of the world in mathematics is to break things up into smaller and smaller problems. So that's what happens here. You break it down into individual triangles or then collections of triangles. And in this case, we'll kind of do the whole A, but we'll start with the kind of concept of the triangle. So the first thing you might want to do is decide that all of your letters are going to be the same shape. And without looking up, I'm going to just assume I can do this in a block that is something like 80. Edit. To make it easy, I'm not going to do that. I'm going to make a block that's actually 100 by 100. So I'm going to go ahead and kind of conceptualize here that I have, ooh, look at that, a block that's 100 by 100. So I'm going to see if I can draw that here. 100 by 100, right? And I'm going to now draw my A inside that block. Right? And we'll see if we can kind of guess. The A is there, and the A is there. And we'll even think about the A looking something like that. So we're going to talk about each letter being defined in a block of 100 by 100 in some coordinate system that, if you're thinking about typical vector or typical Cartesian system, right? This is 0, 0. Later on, you're going to see a Cartesian system that is right-hand coordinate system, though later on you're going to see that some computer graphics starts up here and it's left hand actually, so we're not going to do that. And so we're going to assign these now point numbers. And I'll go back to green here, close. That's point 1, right? We'll call this point 2. We'll call this point 3, point 4, and point 5. And as I draft up this matrix, what I'm going to do is I'm going to do 2, 3, 4 first, because really in many ways you do want to get the concept of these things not only determining edges but also determining faces. So there's kind of, call it an advanced skill, something to shine light off of, whatever you might want to do. And we're going to stick with single strokes here. So we have point 1, 2, 3, 4, 5. We said this is 100 by a 100. So what does that look like in a matrix? Well, I'm going to leave the spot here for point 1, right? So there's going to be something coming up here. And I'm going to leave a spot here for point 5. And then we've got spots for point 2, 3, and 4. Well, let's start with point 2. Well, point 2, if this is 100 across, right, and this is 50, it's going to be at an x of 25 and a y going up of 100. And the fact we have to remember that it actually then has a z elevation. The elevation, if this is x and this is y, this has an elevation of z of 0. That is point number 2. We're going to call that's point number 2. And point number 3 is 50 in the x. And this is incorrect here, so I'm going to go ahead and erase that. I apologize. Let's see if we can do that. Edit, cut. I probably said 50. This is halfway up. And so if I go here, this first point is 25 in the x, 50 in the y. The second point, number 3, I'm sorry, point number 2 is here. We're skipping point number 1. Point number 3 is there. It is 50 in the x, 100 in the y, and again 0 in the z. And that habit you'll see later on, not to confuse the fact that you have to be very repetitive about this scale factor down here. And it is not necessarily standard math, but it is standard computer math to talk about the scale factor. And finally, we look at point number 4, which is, once again, it's 75 in the x, 50 in the y, 0 in the z, and 1. And we can finally go down here and remember that our point 1 is 0 in the x, 0 in the y, 0 in the z. And our point number 5 is 100 in the x, 0 in the y, and 0 in the z. So we have here now a definition of each of the points. And we want to recognize or label, but this is basically a, I don't know, a point matrix, if we want to call it point matrix, with a 0, 1 scale factor. Just as often in many systems you do not include the scale factor, but the reason why you're losing the scale factor is because you want to go back to 2nd grade and 3rd grade and 4th grade and 5th grade and 6th grade, at least in the everyday math curriculum, and remember that we want to now apply some transformations, and those transformations are going to be things like translate, rotate, reflect, and these in fact are the rigid transformations. Eventually you're going to see there are transformations like shear or project, and they're all going to be in matrices that look very similar to this, but which will always be starting with the 16 place matrix. All right. This is going to be a point matrix, and this is going to be a transformation matrix. So by applying this to that, you get it to move or rotate, and not just in 2D space, but in 3D space. So there is some efficacy to beginning with 3D because kids do understand that they do 3D, and they can learn to lock rows. However, you can also very often do this in just 2 by 2. I would recommend against it, so a transformation. So the transformation, I'm going to try to see if I can use the system here to use very light numbers. Begins always with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. Something called an identity matrix. And we will then cover how we go about applying this to that single letter to perhaps shift it so you're dealing with the next letter, B, C, D, which you would want to translate. So let's talk about, before we end this video, what is locked inside this matrix. First off, these numbers generally don't change. They're there to keep the concept of matrix multiplication correct. This here, this subset of the matrix there, is your scale and rotation matrix, and this one right here is your transformation vector. And so if I want to move all of these nodes, these edges of the intersections, I guess, of the vertices of the letter A, if I want to move them 100 in the X, I just go ahead and see if I can go back here and go to color and get something there. I go ahead and change this to 100, 0, 0. I multiply this times that, and I get everything shifted. Later on, you will realize that you have translation in the X, in the Y, and in the Z, even on the TI-83 calculator, and then you can do rotations about any number of axes. Right around here is where you start to get students to just play with numbers. There are other better places to do it, right? But then maybe they go out to the web. Mesh Lab does it. SketchUp does it. But having them see it on a calculator that's flat and somewhat devoid of an ability to go out and waste your time, good or bad, on the internet, by showing them how to go about doing this and having the numbers change, you really can perhaps get over the fact that the TI-83 calculator is old technology, but old technology is not necessarily bad. Realistically, you can do this in class by hand if you need to. And I would recommend doing it for translations. When you can get into rotations, it might be a bit odd. So to summarize, we think of points as vectors, and vectors look like this, X, Y, Z, but then we add a 1 here to keep track of the scale, and then we think of transformations as matrices. That said, I will go ahead and show what happens to the numbers as we start applying some transformations. I will avoid the connect the dots for a separate video to try to keep this within the kind of 3 short videos that explain how to go about some of the theory here to go to the point where you can write stuff like, let's see if we can use a good, all right, how are we going to do this? I'll use Marist again. Use yellow, and then I'm going to use a brush size. So Marist is number 1. All right, so there's our goal. And of course, our goal is not to draw that. Our goal is to have it move, or in fact rotate in around three different axes. So that's what we're doing. Thanks for listening. This has been Mr. 13 Things, and I'll see you in the next video.